In this video we will cover the AiMalgam control panel. To open the control panel at any time, you can simply go to your toolbar, select AiMalgam and click on Control Panel. A new window will show up. The first tab on the left hand side showcases the asset viewer, displaying all graph settings and node settings for your AI. The graphs list displays the names and the node amount for each graph. You can also sort the list by name or the node amount, either ascending or descending. When adding a new graph while the control panel is open, make sure to check the refresh button. The checkboxes on the left hand side help you to select the graphs you want to delete. To do so, finally press the delete checked button on the bottom left. As hinted in the delete pop-up, the undo redo history will be cleared as well, so keep that in mind. Below the graphs list is the node settings list. And one thing I almost forgot is that you can select each list item and it will be showcased in your projects window. This can be very helpful if you forgot where you placed your graph settings or your node settings, as it is also possible with the node settings viewer. Continuing with the node settings list, you can also sort them by name, but also additionally by the graph amount, the connection amount each node has, and its setting type, again ascending and descending as well. Notice the list body updating after you change the sorting. You can also filter the displayed nodes by, for example, showcase only nodes that are contained in at least one graph or in no graphs at all. And the same goes for their connection amount. Either display nodes that have at least one connection or have no connections at all. This can help you with deleting nodes without risking that any connections are broken. Although the scriptable object can still be referenced somewhere, so always keep that in mind as well. Similar to the graphs viewer list, you also have to check the refresh button if you add a new setting and the control panel is open at the same time. To delete node settings, it is also the same procedure. Just check the desired nodes you want to delete and finally press the delete button. Now I will explain you the code creation part, where you can create your custom AI logic, such as engines, actions, conditions, deciders, descriptors, and comparers. If you want to create a completely new independent node, I will also explain that at the end of this video. The first section manages the creation of an action pack, which creates 4 dependent classes, being the action, the engine where the action must run, the blackboard for data injection management, and the action setting that represents the running action, the engine. By default, the action will be an abstract class as well as the engine. And if you check the boxes below to create a sub-action and sub-update engine, there will be 2 example scripts that inherit from those created classes. On the right hand side of the naming field, you have to select the path where the script should be generated. For now, I will create a test folder. Make sure to define a path for each script separately. You can also rename each class and its file name. If you are done, simply press the Create Behavior Pack button. As you can see, the scripts have been generated in the folder I have assigned them to. Let's take a look what has been generated. You can find the API documentation in the video description and in the manual as well, if you want to look further in the code architecture. At first I will show you the generated base action class. As you can see, the file and class name match the name we put into the input field before we generated the script. Each custom action class must inherit from the AiMalgam base action class and define a blackboard class they need for operation. You can also override the base events and call them if you initialize, or another event would be to dispose the action, where you would call it in your overridden dispose method. Here the settings property is overridden to reference the custom specific settings we have also defined in the actions creation pack. The same goes for our engine that in the end will host this action. Each action must call its base constructor, otherwise there would be a compiler warning anyways. Here you can already see some overridden methods of the base action, such as the initialize, restore and validate method. If you don't have an abstract action class, you must also inherit the run method, which we will see in the example sub-action we checked to create. The initialize method is called once when the action is injected into the engine and is about to play or run. The restore method is only called if you set this up in the respective action setting and also only after disposal. And the validate method is called before each run to indicate if the action should run in the first place or if we should wait another tick of the hosting engine. As you can see, this sub-example action is not abstract and inherits from our base abstract action, calling its constructor as well. The most important section here is the run method, where you implement your action's logic that is run in the engine for the AiMalgam instance at runtime. You can also see that the blackboard is given as a parameter, as well as in the other methods we have inspected before. This helps you to deal with specific data types your action needs. For example, targeting other entities that were dynamically added in the game environment. Basically, instant-based, dynamic, runtime data that cannot be defined in a global scriptable object before runtime. Make sure to define a success state for your action, since it may be used in a async multiple decider decision system where it depends on success of actions that have finished to either abort or continue the actions queue. You can also set is done at any time you want to indicate if your action is finished. Otherwise, the engine handles the core settings lifecycle for the running action. As you can see, the blackboard we generated doesn't have any values yet, but you can of course enhance it if you need it. Also note that the blackboard must implement the AiMalgam blackboard interface. Up next we look into the generated engine, which inherits from the AiMalgam entity base engine, setting the generated action and blackboard as the generic arguments to clarify which actions match to which engines and settings and how they will be mapped finally via the AiMalgam entity. The mapping is done via a caching procedure, so don't worry about expensive reflection calls at runtimes for each action setting that needs to be converted into an action by finding its correct engine from multiple ones. If you don't want to handle multiple engines for each new action type, you can also define one big engine and one big blackboard and use the switch statement to create different kinds of actions that map to the same engine. It is important to override the apply settings method so you can create your custom action here to finally add it to your actions queue that will be run in the tick method. You also need to define the apply settings result to tell the decision system if creating the action was successful or not. If successful, it is important to add the action to the queue. Here you can see the switch statement where you can create different kinds of actions that inherit from the base abstract action to save up some extra engines. This is also done in the follow action implementation and the spotting action implementation. Finally, call this method for AI graph debugging to know if the action setting passed or not visually. And here's the sub-engine example calling the tick method each update frame. And as a result, the actions run method will be also called each update frame unless you set the settings up so they will be only called once every X milliseconds or seconds or minutes. But in this case, each frame the validation is called, the run may be called, and the actions list is handled, like adding the new actions from the add queue or removing actions from the remove queue. This is basically the job of the tick method. Before calling the tick method, you probably want to adapt your blackboard data. For example, if you want to use delta time or fixed delta time, you would assign it right before the tick call. This is done in the follow engine, flee engine, and animation engine as well. Now we come to the generated settings. Above these settings you see the create asset menu to help you with creating the setting anywhere in your project via the context menu. You can define a custom node width, or if you want, you can use the node icon attribute to define a specific icon as well. Also consider using the node visibility attribute to set its visibility priority in the graph editor. The custom action settings inherit from the AiMalgam base settings for engine and also define the same action and blackboard as the generic arguments. This is also needed for mapping the action setting to the engine, which then converts the custom setting to the respective action that is finally run in the engine mono behavior for the AiMalgam entity. Again, no expensive reflection is used for each mapping comparison. That's it for the action behavior pack overview. Make sure to check out the API for more information. Next, we will create a custom descriptor class, which is also a mono behavior and acts like a data extension for the AiMalgam entity that represents runtime and instance-based data. Similarly to the create actions pack, you can also define the path and the name of the class you will generate. As you can see, there are no real complex methods or fields in the descriptor. It's just a template class you can define your custom data in or describe the entity in a more complex manner. For example, describing the health of the entity or relationship or mood or whatever you want that fits your game. Up next we have the condition class creation section with two new different options below it. One being to define if a descriptor is required for the condition and which one, or if the condition should be independent of any descriptor. You can select every available descriptor in the project as the required data container for the condition to execute. By every available descriptor, I mean the descriptor type, not the actual mono behaviors that are out there. Generating the script works the same way. Just press the create button below it. In this case, I forgot to set the folder path, so it is generated at its default path, which is the root assets file path. Let's drag it to the test folder. And we see an error message popping up. This is because we dragged the script into another folder where another assembly definition is located, which does not reference the assembly where the combat descriptor is located. In this case, the demo implementation assembly definition. So if you ever come across the same problem and use assembly definitions, make sure to reference the correct ones. One being the core AiMalgam assembly definition, and if you use the demo implementation scripts, you also have to reference the demo AiMalgam assembly definition in your custom one. For this example, I simply drag the script into the folder where the demo assembly definition file is located. And that fixed the error message. The comparer script generation has a very similar setup, if not the same. Now let's create an independent condition that does not need a descriptor for condition execution. And here is the independent condition script we have generated. As you can see, it contains an overridable method where you can implement your custom condition checks you can then later use in the graph editor. With custom conditions, the AI really comes to life because you can branch to different actions in your decision tree. You can set up custom fields in the scriptable object condition to check the target AiMalgam entity against. As you can see, the method contains two parameters, both being of type AiMalgam entity. The first one is the entity you want to check the condition against, and the second one is there to indicate which entity called this condition, and if this condition setting may be marked valid or invalid in the graph with the call you can see in line 20. The condition requester entity must match the hosting entity of the selected decision system in order for you to see the markings in the graph editor you want to debug or view the colorings in. It's mainly for visualization for you. In most cases, the target AiMalgam entity is the same entity as the condition requester entity. It may differ in special settings like spotting settings, or if you implement your own condition checks from within action scripts. The other generated condition script uses a descriptor as a dependency. As you can see in line 20, it needs to get the respective or required descriptor from the target AiMalgam entity by using its hash, which is automatically generated if you simply inherit from this AiMalgam base condition for descriptors class. As you can see, no reflection is used calling this condition to get the desired descriptor. We are using a hash mechanic for that. Those descriptor dependent kind of conditions are especially useful if you need more data from an AiMalgam entity rather than just its states or base information. So you can use the descriptors as runtime instant-based data containers. For example, to read their health or mood or anything else you have implemented. Up next we will look into the comparer node settings. Again, I will create two versions, one being dependent of a descriptor and the other one being independent. It is basically the same procedure. Let's open up the generated files. As you can see, it contains two overridable methods, one being the compare method and the other one being the getResult method. Here you can define how the two AiMalgam entities will compare against each other. And you have a third AiMalgam entity where you can check those two AiMalgam entities against. So the first and second parameter in the compare method are basically the list elements you want to compare, and the third one, being the check against AiMalgam entity, is always the same. So you can, for example, sort or compare the entities by distance to the check against AiMalgam entity. This is especially useful if you want to implement a targeting comparison. The getResult method in its base class basically sorts the given targets list, either the original one or a copy of it, as it is asked in the third parameter, and returns the winning entity. So the procedure is the targets get sorted using the compare method, which you define here, and the first element is then returned. Usually you don't want to override this method, but if you have any custom logic you want to implement here, feel free to do so. The descriptor dependent compare class inherits from the AiMalgam based comparison for descriptors class, defining the AiMalgam spot descriptor as the generic argument as we have set it up in the code generator panel. And basically it is the same idea, with the difference that we want to compare the entities by their descriptor. And again, a helpful descriptor type supported hash is accessible for us. We don't have to define the hash, it is all done automatically in the base class. Again, you shouldn't need to override the getResult method, but this is up to you. Lastly, we have the decider generation section. Here we can create two different types of deciders, both inheriting from the same root but with a different direct base class. First things first, let's set up the generation path and the name. The main difference between those two decider classes is that one implements the same structure the general deciders use, like the single decider or multiple decider, random decider, where it can either represent a branch leaf decider only leading to action settings, or a normal branch decider leading to other deciders. If you want to implement from the root, you can create a custom procedure, maybe even a decider which can both select action settings and other deciders as their children. Another special decider which does not inherit from the base decider is the subgraph decider, for example. Let's take a look at the decider which inherits from the base decider. As you can see, its two main overridable methods are the branch and leaf traverse methods, with the branch traverse methods going through the decider list, which is found in its base class, and with the leaf traverse method going through the action settings list, which is also found in the AiMalgam base decider. So you can implement your own custom priority or traversal logic in the respective method and how the lists are handled. For example, the random decider randomly picks an item from the list, and the score decider selects the list item which has the highest condition result score. Calling the apply branch leaf to entity method found in the AiMalgam base decider from the custom leaf traversal method initiates the setting to action conversion if these settings were validated and the respective engine was found on the requesting AiMalgam entity. So while traversing through the leaves, the actions are already being queued to the respective engine, if found, of course. If you want to traverse through other deciders, it is important that you call the root traverse method. Don't forget to add the traversal information to the decision parameter object and return it. The decision object basically stores information about which decider was traversed and if it was successful or not. In the end, it will be emitted in an event from the decision system mono behavior. Let's look at the special decider we have generated, which inherits from the AiMalgam decider wrapper, which is the root for all deciders. As you can see, this decider only overrides the root traverse method, so there is no leaf or branch traverse method in the first place. It's only existing in the base decider. In the root traverse body, you see the implementation from the subgraph decider, but you can implement your custom traversal methods that are different from the default ones as used in the single decider or multiple decider, or generally how the base decider operates, as we have seen in the previous class. Make sure to handle the isLeaf property correctly, to not mess with other decider nodes. You might be wondering if the custom created node settings will be displayed in the graph editor. I will show you that this is indeed the case. As you can see, the newly created decider settings can be added as node instances into this graph editor, or in any other graph editor as well. This can also be done via the context menu. Let's generate a few more node types and I will show you that they will appear in the graph editor as well. You can also see where the custom decider scriptable objects were located, right beside the AiMalgam node graph. If you want to change the icon of the scriptable object and the script file, simply navigate to the top left corner of your selected script file. Note that this is not the same icon displayed as in the graph editor. It is there for the project view. To display another icon in the graph editor, you have to use the node icon attribute above the class header. You can find the icons used in the resources folder. As you can see, you can also create the node settings from within the project context menu. This is because we added the create asset menu attribute above the class header. As you can see, our newly generated custom condition is also accessible via the Manage Assets side panel. You can work with your custom node settings like with any other existing node. You can connect them, move them around, delete them, change their settings, basically the same as with any other node. Now, what if you want to create a node setting that is completely different from the existing core architecture and is also not present as an option in the code creation control panel? Let's get right into it and do exactly that. First, delete the default class contents. Let's inherit from AiMalgam node, which is a necessity to be displayed in the AiMalgam node graph editor. Now let's take a look into some attributes for the class header. The first one being the node appearance attribute, which indicates when the node setting should be hidden or displayed. If you set it to minimum, the node setting will be always visible. And if you set it to maximum, the node setting will disappear at average or minimum and only appear if the graph editor sets its visibility to maximum. The node appearance attribute will be inherited from the deriving classes. Up next we have the Unity create asset menu attribute, which is needed if you want to create the settings from within the project's context menu. This attribute will not be inherited. You can define the file name and the context menu path to access the creation of this node setting. Next we have the node icon attribute. You can define the resource path for your icon you want to display in the graph editor. As already mentioned, this is not the same icon that is displayed in your project view. Furthermore, this node icon will also be inherited from subclasses. To enable connection to other nodes, you need to define an output port. This port field must be of same type the class is, and also needs the output attribute. Another class header attribute is the create node menu attribute, where you will define the context menu path in the graph editor. So it is a different run from the project context menu. Here you only need to define the context menu path and not the file name. Also, this attribute will be inherited as well, so you don't need to redefine it for the subclasses. Let's create a node setting instance and see how it looks like. Generally, we want to hide the output field since it is only used in the graph editor. You can use the node attributes for that purpose. As you can see, it is now in the fold out area. Now let's see how the node setting looks like in the graph editor. As you can see, adding it to the grid area causes now issues. It also displays the settings icon we defined in the node icon attribute, but it does not appear in the side panel yet. Let's fix that. We must add another interface that implements the AiMalgam interface. And then the node setting must implement our custom interface. Let's check it out. And as you can see, we have a new slot in the side panel. Although the naming does not look very pretty. You can change that if you rename the interface or if you add the naming AiMalgam as a prefix of your custom interface. Now, what about input ports? To add a simple input port for a single field, the type must in the end have the AiMalgam node as a root ancestor, and you need to add the input port attribute for this field. You can also define the connection constraints Generally, it is recommended to define the inherited any constraint, so you can connect to node settings that either are deriving from this class or are an ancestor of this class, or rather from the type you want to connect to. In this case, it is this class. Oftentimes, single input port fields are not enough for a setting. So let's add a input port list. For that, we must build a serializable list wrapper. Inherit from the list wrapper class and define the list item type as its generic argument. Don't forget to mark it as serializable to be displayed in the graph editor and in the inspector as well. Similarly to the single input port field, you need to define a field for the list wrapper, but choose another attribute. This time it is the reorderable node list attribute. Also tell it the list item type there as well. It is important that it is exactly the same item type, otherwise there will be errors. Now let's take a look at the result. As you can see, the node body now shows some input ports. Connecting nodes now works the same as with any other node setting out there. The context menu actions for this custom node also work. That was basically the most important stuff for the node setting. But now I will show you some interesting methods you might want to take a look at. The onClose method is called if the graph editor hosting this node gets closed. Same goes with the onOpen method, only that it is called when the hosting graph editor is opened. Sometimes you want to handle the column marking in the graph editor when using AI debugging. If your node setting is not called within the normal traversal, it might appear as white always, so you might want to stop the reset marking here or handle the marking separately to synchronize with the tree traversal. For that you can subscribe to the onPrepareDecisionMate event and the onDecisionMate event, both of which you can find in the decision-making system MonoBehavior. This is a difficult task though, since you need to keep track of what component is selected by the developer in the Unity editor. The onNodeChange event is called from the validate method, but you can also call the notify onNodeChange method instead of overriding the event and calling it yourself. You also don't have to inherit from the AiMalgam node directly. Here, for example, is a helper class that also displays editor-only node fields like the name and description field. This is optional. As you can see, the input field and the input port list field are rendered above the box groups. Let's fix that. You can simply define your own box groups by using the naughty attributes box group attribute and change the name of it. And as you can see, the input fields are now in a separate box group. As always, you can press the Show Graphs button to list every graph that hosts this selected node setting. That's it for this tutorial. Enjoy creating your custom AI logic.